Hello everyone, welcome back to the course Deep Learning, Theory and Data Science. I hope everyone had a wonderful family day and a wonderful reading week. Last time we spoke about the topic of linear and quadratic discriminant analysis, and I thought that we would start by reminding ourselves what we talked about last time, since we kind of stopped abruptly in the middle of the presentation. So we started last time by talking about how data scientists love Gaussian distributions. And we then talked about Fisher, who's a genius with a little bit of a dark past, if you read on Wikipedia. Did anyone read on Wikipedia? Or actually, don't say. I don't stir up controversies in the course. So Fisher had this iris flower data set that he was interested in classifying. So it's just a bunch of flowers. And the features in that data set were the petal and the sepal, which I'm probably horribly mispronouncing. And so there's the width and the height of the petal and the sepal. And you have also the species of the flower. And the goal is to predict the species of the flower from these attributes. And what Fisher proposed was what's called, first of all, quadratic discriminant analysis. And quadratic discriminant analysis is essentially assuming that your data, once restricted to a given class, is distributed as a multivariate Gaussian distribution, a multivariate normal distribution. So here you can see, for example, two classes, each is roughly a multivariate normal distributed. And we saw how the classifier decision, the classifier that just picks the class which is most likely given the sample, reduces to a decision boundary which is quadratic. And essentially the choice of the class reduces to some type of a quadratic function that depends on the class means and the class covariances. Feel free to ask questions, by the way, even if it's me recapping what happened last time. So for example, here would be, mu1, let's say, and here you would have mu2, right? And here you would have sigma 1, and here you would have sigma 2. And then we mentioned how in practice you don't have access to these population statistics, as they're called, and you must estimate these population statistics from your data. So you get these empirical estimates, as they're called in statistics. And you just plug these empirical estimates into the formula in the previous slide, and that's how you do classification. And then we mentioned how there is something called a linear discriminant analysis. Instead of quadratic, it's linear. In the linear discriminant analysis, you assume that the covariances of the data are class independent. So all the class covariances are in fact equal to each other. And we denoted that covariance, which is equal for all classes, by sigma W. Why is it called sigma W? Does anyone remember? What does the W stand for? Does the W stand for whole, as Neo says? Does the W stand for win, because you win using this classifier in prediction challenges? Does the W stand for within, as Justin said? Yeah, so it is within, or wait, Willy Wonka. Didn't watch that movie. Is it the one with the chocolate? It is the one with the chocolate, right? Yeah. Is it good? Should I watch it? By the way, previously when we talked about the fifth element, I did a very thorough analysis after the lecture to verify that indeed that lady was from the fifth element, and I was amazed. old one only. I didn't even know there was old one. Okay, so back to the lecture. So this is a W that stands for within, as Justin said. Why is it called sigma within? Within what? Within the collected data? Within a class. Justin seems like an expert on linear discriminant analysis. So it's sigma within a class. What does it mean, sigma within a class? It means covariance of data within a class, right? So it's like covariance of data once you restrict yourself to being within a certain class. And so basically, in this linear discriminant model, you assume that there is a single covariance matrix, which is the within class covariance matrix, and there is a set of class means mu c, right? And then what you can do is you can show that picking the class that's most likely given a certain sample X reduces to a linear classifier, And the classifier in this case is equal to this thing. This is the classifier of a given class. So this classifier has a very appealing form. Does it appeal to you or does it not appeal to you? It does appeal. Okay, so at least one person. LDA is working on the same problem, but the linearity comes from the homoscedastic assumption. That is exactly correct. Yes, yes, yes. It is the same problem, and the problem is classification. And it's basically LDA is a special case of the quadratic discriminant analysis, where you're willing to make this homoscedasticity assumption, which says that the class covariances are all equal to each other, right? And so I want to emphasize again that in this case, the classifier is this thing, sigma W inverse multiplied by the class mean minus the global mean. And then we discussed how in this specific case, the choice of a class, let's say if you pick a certain point in space and you have to choose, you have to predict the class based on this model, then the choice of the class actually reduces to picking the nearest class mean after you transform your data by sigma W minus half. So here's an illustration of this. So here you can see three classes, the blue, the green, and the yellow/orange. And is there a name for this color? I feel like it's not yellow or orange. Usually there's many words for many colors, but I just know the basics. Does anyone care to enrich my, wow, saffron, amber. You guys know so many words. And so basically you can see how the shape of all of these covariances is equal to each other, right? That's why in this specific case, you have the homoscedasticity assumption being satisfied, right? And I'm saying that the noise here is anisotropic. Does anyone know what does anisotropic noise mean? I'm just teaching you words that sound fancy so you can impress your friends later with these words, you know? Not a circle is a beautiful definition. Thank you, Neo. Yes, anisotropic just means not a circle, not a sphere. It's a covariance which is not spherical. Yes, Andrew. Yes. And what happens is that if you apply the transformation sigma W minus half, then you're essentially making all of these non-spherical noise distributions spherical, right? After the application of this transformation, all of these anisotropic noises become isotropic noise, right? Do you see why multiplying by this would create isotropic noise? Or you don't see? So there's, I think I mentioned this last time, but I feel like maybe I wasn't too clear on this point. So imagine you take a certain x, imagine you look at the distribution of x given y, right? We assume that the distribution of x given y is normal with a mean mu c and a covariance sigma w. Does anyone have any objections to this assumption? Now would be the time to say so. Okay, no objections. Now imagine the covariance is the same for all classes. Yes, yes, yes. It is the same for all classes. In linear discriminant analysis, the covariance is the same for all classes. And so imagine if we look at A times X given Y. Does anyone know how is this distributed? If A is just a fixed matrix of my choice. So this is something you hopefully have learned in probability courses that you've done or haven't done. No. Yes, Justin. So this is equal to A mu C. So it's distributed as normal with a mean A mu C and a covariance A sigma W A transpose. So if you don't believe it, try to prove it, okay? Now, imagine if we pick, A to be sigma W minus half, we get sigma W minus half times X given Y is distributed normal sigma W minus half times mu C with an identity covariance. Isn't this magical? Do you find this magical? I think at the very least, Luke finds it magical. So this is magical because you've managed to take this unpleasant, no one likes anisotropic noise, right? Like whenever you see anisotropic noise, the first thing you should do is just make it isotropic because people like isotropicity. It's very pleasant to work with, right? And so once we transform our features through this transformation of sigma W minus half, we get this beautiful isotropic noise now, right? And after we have this beautiful isotropic noise, if I give you a certain coordinate, a certain example, right? A certain example here, which is sigma minus half times X, and ask you, it is called noise whitening. That is correct, yes. If you ask yourself, if I ask you, can you please predict what a class does X belong to? What would you do? You would just see which class mean does this X, which class mean is it closest to, right? Does anyone know what's the word for what's implicitly being constructed here? So basically, the classification procedure is based on this tessellation of space, right? This tessellation of space, which is basically something like this thing, right? Verneuil cells, says Tristan. I feel like this is one of those bingos, you guys should have like something, and then whoever gets 5 or something wins the lecture. Maybe we can arrange this for future lectures. This is indeed correct, Tristan. Yeah, bonus mark. So this is indeed a Verneuil tessellation. That's one way of saying what's happening here. And so basically, I just want to recap this thing again, just to make sure we understand. After you transform by sigma W minus half, right? If I give you an X, all you have to do is do X minus the class means, multiply by sigma W minus half, and try to find the class C that minimizes this L2 norm. Does this make more sense now, or is this still not very clear? This thing. Clear to a certain extent. Okay. Now, yeah, so here I was trying to illustrate that Oh, okay. So here I was trying to illustrate that if you take all of these class means, you can average them and you get something called a global mean, right? A global mean. And this global mean can be connected to one of those class means, and then you get mu1 minus mu g multiplied by sigma w minus half, right? So really, this is a fundamental quantity. I know, Karen, you want to correct this. I know. I didn't update the slides. I'm sorry. I did update them on the website, but only you noticed the mistake. So, you know, there's basically no mistake if no one else notices. So here, this is a fundamental quantity. Why is this a fundamental quantity? Because this is a difference between your mean and a global mean, right? And it's multiplied by sigma w minus half. Can anyone perhaps use their voice and explain to us what is so fundamental about this quantity? Why is this quantity the only thing one truly cares about? Why is this my favorite quantity in this whole presentation, if I had to choose one? It's the classifier. It's very close to the classifier. The classifier is, oops, sigma w. So classifier WC is sigma w minus half mu c minus mu g. So it's a cousin of the classifier. It's the classifier if you undo the transformation, right? If you undo the transformation. But I mean, Reza says it's a threshold for distance, not quite what I'm trying to get at. So let me give you a hint. Let me give you a hint. Does anyone know what is this quantity? What does mu over sigma indicate to you? Or maybe it has no significance to you. It's just normalized mean. Yes, signal to noise. Yes, Radon-Nikodym measure. I'm not sure about the last, yeah, I'm not sure about the last one, but it is a signal to noise ratio. So think about this in the following sense. There's two things that are important in life, signal and noise, right? You want to maximize signal, you want to minimize noise. In this specific case, the signal is how far away are the class means. You want the class means to be as far away as possible. Why? It is the yin and the yang. We're back to philosophy. So you want the class means to be as far apart from each other as possible. Why? Because you want the probability of misclassification is related to the distance between the class means, right? Imagine if you had something like a, you know, this is, let's say, let's do it 1D. Imagine you have here a Gaussian bump and here you have a Gaussian bump. And compare this to the case where the Gaussian bumps are almost overlapping. So here you would have very low misclassification, whereas here you would have very high misclassification, right? Now, which one do you like? You like the thing that makes you win competitions. What makes you win competitions? When you have low misclassification error, right? So we want low misclassification error, which means we want the means to be far apart. But notice that it's not only about the means, because the distance between the means by itself is meaningless. You must normalize by the standard deviation of the noise, right? You must normalize the distance between the means by the width of the Gaussian. Otherwise, there's no reason to be looking at means, right? The quantity, the difference between two means is insignificant if you know nothing about the width of a Gaussian. Does this make sense? So basically, this thing is this distance, right? It measures how far away is the class mean from the origin, and this thing is normalizing the mean. Normalizing the mean. So this is why this is called signal to noise ratio, I guess, in a double E setting. It is a normalized mean. That's also correct. Does anyone have any question? I have another slide that makes the same point even clearer. I can see someone wants to speak. Yes.
Professor, can you explain the mean again? Is that the mean between two bump?
So maybe I should clarify. Thanks for the question. Basically, here you have the global mean. So this is mu g. And here you have the class mean. So that would be like mu1. And this would be mu2, right? So in the two-class case, you want, for example, mu1 minus mu g to be as far, you want mu1 to be as far away from mu g as possible. And you want mu2 to be as far away from the global mean as possible.
I see.
It's in the two-class case, it's equivalent to saying that you want the two means to be as far away as possible from each other.
Okay.
If that makes sense.
But does that imply if mu g is away from mu2, then it will be closer to mu1?
So recall that the definition of mu g it's the global mean. So it's literally between mu1 and mu2, right?
Okay. Yeah. Okay.
So you can think, to simplify your thinking, you can just imagine that everything is centered at the origin of the universe, which is, I don't know where it is, but everything is centered at 0, let's say, right? So the only thing that you can do is change how far away, both class means are from the origin, let's say.
I see.
Is the norm of this quantity the same for all mu I? The answer is no. That's a good question. So let me try and show you another. What is this? Let me show you another way of this. Also, we discussed in the previous lecture. Maybe I can reiterate this idea. So here you can see how there's two classes. There's the blue class and there's the red class, right? Blue class, red class. Imagine I ask you to find a direction that once you project the data onto that direction, the classes would be as separated as possible. How would you do that? So imagine you take this blue class and you project it onto this direction, right? Imagine this blue class is Gaussian. If the blue class is Gaussian, what do you know about the distribution of these points once they're projected onto this line? Still Gaussian, right? And how do you know that? How do you know they're still Gaussian? No. So it's again the same theorem that I was alluding here, right? If you multiply X, which is a Gaussian, by a matrix A, it remains Gaussian, and the only thing that changes is the mean and the covariance are being multiplied by this A, right? Does that make sense? It's correct, Jim showed it's correct that it's a projection matrix, but it's even more general than that. Whenever you take a Gaussian and multiply it by something, it still remains a Gaussian, as long as that something is fixed. It's a useful theorem for life, you encounter this in many places. Just to make sure I understand, is each dot an image and the color indicates which class the image is? That is precisely correct. And if so, then any overlap means that an image could be classified one class or another depending on some probability. That is, to a certain extent, somehow correct. But basically, you're asking if there is an overlap. If there is an overlap, it means that the things are not linearly separable, right? So there is no way to separate them in train, is how you would say it, in train. In the distribution, you might have a bunch of other points, right? But even if they're overlapping, it means even in train, you cannot separate them. So again, let me reiterate. This is a one class, right? And you can think of each dot as a different image, like Gina said. And basically you take all of these examples and which are vectors in some high dimensional space, and you just project them onto a line. After you project them onto a line, you get points which are still distributed as a Gaussian. I feel like I'll just repeat this sentence as many times as possible this lecture, just to verify you remember. You know, I think the point of these lectures is you remember important things for life. So this is one of them. Maybe write it on your hand or something. Look at it twice a day until you remember it. And then notice how here there is a plot, right? What does this indicate? Why am I plotting something like this here? What is this? Why is there some bluish thing here? What am I trying to convey through this bluish thing? The variance, yes, and the mean, right? So here you can see the mean, which is just W transpose times mu1, where this was mu1, right? So after you project the mean onto W, the new mean is W transpose mu1, and the variance here, right? The variance is what's written here. The variance is equal to W transpose times sigma times W. And you can do the same thing for the other class. And then you are tasked, what? I thought there is some subtlety to this, though. We have assumed that the features are jointly Gaussian, so then linear transformation is always Gaussian? I'm not sure I understand. We assume that the features are jointly Gaussian. Yes. When you say jointly Gaussian, I think you mean multivariate Gaussian. So then linear transformation is always Gaussian. Yes, that is also correct. So after we project all of these data points, can you judge whether the training data is linearly separable in higher dimension by only observing the projected distribution? The thing is that at this point, we haven't specified what's the correct direction to be looking at, right? We haven't specified, but what you're saying is correct, because if you find the direction W, and after projection to this dimension W, the two distributions are separated from each other, it means that you found a direction in high dimensional space that separates the data. So what you're saying is in fact correct, Amireza. You can judge whether the training data is linearly separable by only observing the projected distribution. I know, but currently we're looking here at a sample, at a fixed sample. If you're asking about an infinite sample, then yes, it is not correct. I think your understanding is precisely correct, Amireza. So at this point, notice that the thing that you care about is finding a direction W that would maximize the distance between the means, mu1 minus mu2, once projected onto the direction W. And also, you must normalize this mean by the variance of these bumps. Again, there is no meaning to a mean. There is a meaning to a mean divided by a standard deviation, or a mean squared divided by the variance. And that is indeed what Fisher did. So Fisher said, let's define a function j, which depends on a direction W. And let us define a criterion, which says how good is this W. So this criterion is equal to a mean as function of W squared divided by the standard deviation as function of W squared. So this is signal to noise ratio. And what Fisher said was, let's maximize this. Let's pick the direction W that would maximize this quantity. And what we've done in the previous lecture was to show that the optimal classifier is this classifier. This classifier maximizes this criterion. This is, does anyone recognize what this thing is? Have you seen this in your past? Maybe in the immediate past? Does this look somewhat similar to anything that you've seen very recently? That was WC, that is correct. Yes, thank you. Thank you, Gina. That is the WC of linear discriminant analysis. So linear discriminant analysis is maximizing the Fisher linear discriminant. Okay. So here's the proof. I won't go over it again. Okay, and this is where we stopped last lecture. And this is when another individual comes into play by the name of C.R. Rao. Here you can see a picture of C.R. Rao. Now, what C.R. Rao did was he generalized the linear discriminant analysis to multi-class, to many classes. How did he do that? In order to generalize the linear discriminant analysis to many classes, the first thing you need to do is define this quantity, which is extremely important, the between class covariance. What is the between class covariance? The between class covariance is the covariance of the class means. Does everyone see that this quantity is a covariance of class means? So how do we see that this is a covariance? So notice that you have here a sum over a bunch of vector transpose, where from each vector we're subtracting the average of all the vectors, right? So the way you see covariances in probabilities, you see expectation over x minus expectation of x, right? Does this look familiar to you, this equation, right? This is a covariance of x in probability. But we're focusing on empirical samples. Amireza says it's like considering centers as individual points and calculating the empirical covariance. It's not like, it's precisely what you said, precisely. So you treat the class centers as points, as individual points, and you calculate the empirical covariance for those individual points. Does that make sense? So here you can see the mean of all the class means, right? And you're subtracting from each one of the class means the mean, and you're doing a sum of the outer products. Does anyone have, does anyone agree that this is a covariance of the class means? Are there any objections? Okay. Now with this, so this is the between class covariance. And I remind you that we also have the, could you explain how the pi's relate to the typical expectation integral? So the pi c here are the probabilities of each class. So in this expectation right here, when you're doing it, so when you're doing expectation, as Karen says, you have an integral of probabilities times quantities, right? So in this specific case, the probabilities are pi c. It's just the probabilities of the classes. But, you know, for our sake, in all, whenever I'll talk about this, I'll always assume that pi c is just 1 over the number of classes. So if you don't like this, just ignore it. Just ignore it. Now, recall that in addition to the between class covariance, we also have the within class covariance, which was sigma w, right? See, between class, within class. Now, what Rao said was, in order to generalize the Fisher linear discriminant analysis to multi-class classification, let us consider this function. For the sake of this lecture, you can think of it as being just finite. I'm not aware of anyone who generalized this to countable or infinite. So just assume it's finite, okay? So what Rao did was proposed the following objective: Jx function of capital W, okay? Capital W is a matrix. And this is the matrix that is going to multiply your samples, your, let's say, images. Now, the proposed function is as follows. You take the between class covariance, you multiply it by W on the left and on the right, and you take the within class covariance, you multiply it by W on the left and on the right, and in both cases, you calculate the determinant and then calculate the ratio. So it's a ratio of determinants. Does anyone see why is this extremely intuitive? Why is this a correct quantity to be calculating? Why would Rao think of this? Let's start with a simpler question. What would the following quantity mean if I just looked at sigma b determinant divided by sigma w determinant? What does this quantity mean, the alternative quantity in red? The alternative quantity in red, first of all, what does it mean to do a determinant? What does it, when you calculate a determinant of a covariance, what does that measure? A determinant of a covariance is just measuring how large is the volume, right? That's the intuition. If the determinant is large, it means that the volume is large. If the determinant is small, it means the volume is small. You can think of it as different ways, but that's one of the ways to think about it, right? So essentially, if the determinant of a covariance is large, it means that there is large variance. If the determinant is small, it means that the variance is small. This quantity is independent of W, Neo. That is correct. I'm just taking it to a side story, try to explain what's the intuition. Okay? So exactly, so it's like a ratio of two volumes, exactly. So basically here you're calculating the ratio of the class means, and here you're, sorry, the volume of the class means, and here you're calculating the volume of the within class covariance, right? So the intuition is that this is, again, a signal to noise ratio. You're just measuring how large are the class means divided by how large is the noise. Do we have to use the determinant? No, no. I can think of various ways to calculate how big is a covariance, right? For example, does anyone have any suggestion for an alternative quantity instead of the determinant? What else could we use? What's your favorite function to apply on a covariance? There's only one correct answer. If I give you a covariance now, no. What's the most pleasant function to apply on a covariance? It's not the function norm, not that one. Just the trace, right? You could do, for example, the trace, yeah. Trace sigma b divided by the trace of sigma w. Don't you love the trace? Trace is my probably top 5 favorite operators. Maybe even top 3. So basically, this thing intuitively is kind of the same thing as this thing. It's just measuring how large are the class means compared to how large is the noise, right? Now, in this case, what is this quantity measuring? Yeah, that is correct, Amireza. But in this case, we're talking about covariance matrices, so all eigenvalues are positive, right? So Tristan says the correct answer, which is the same thing after a change of variables. Exactly. So here, this is literally the between class covariance of the features or of the data after you multiply by W. And this is the within class covariance of the data after you multiply by W, right? Does this make sense? W transpose, yeah, it is. Sorry for the mistake, Neil. That is correct. So basically, in simple words, why did Rao choose this function? Because this function is measuring how good is the matrix W in terms of the signal to noise ratio of the data after you multiply by W. Isn't that extremely intuitive and clear and simple, to the point where you could have done this if you were just alive at that time? Maybe not. Now, signal to noise ratio for multi-class classification, and one can prove that if you optimize this, if you maximize this function, the optimal classifier would be this. Does this look familiar to you? Again, I should ask. Does this look familiar to you? Have you seen this in your immediate past? W is a matrix, that is correct. Oh, but when I say WC here, I mean the cth row of W. Does this say? Okay, yeah. So at this point, hopefully we understand linear discriminant analysis in the single class case and the multi-class case. There's a question. Is there a relation between signal to noise ratio thing and the optimal transpose of some kind between the two projected Gaussians? I'm not aware of that. There might be, I'm not aware. I'm not aware. Not aware. That's a good question. So LDA is in fact very much related to PCA. PCA is just eigenvalue decomposition, right? So if you think about PCA just with one direction, right? Imagine you take data, you know, red class, blue class, and you do PCA with rank 1. What do you get? You get a direction that is maximizing the variance of the data projected to that direction. Does this make sense? Have you seen PCA in your life? I assume you've seen PCA in your life. You have not seen PCA. Okay. What is PCA? Okay. My assumptions are, as always, incorrect. PCA is a fancy word for eigenvalue decomposition. So PCA is equivalent to eigenvalue decomposition. And when a person says PCA, I think some people will get mad at me for saying that, but no one has ever convinced me that there is a difference between PCA and eigenvalue decomposition. So I'm sticking to my beliefs. Now, yeah, for yeah. I've never seen anyone do PCA for a non-square matrix. So basically PCA is just eigenvalue decomposition. And if someone says PCA with the parameter K, let's say, it means the eigenvalue decomposition of rank K. Why would it be useful to maximize the variance of the whole set? Yeah, the covariance, yes. Yeah, sorry, I should have said that. So if I give you a data set, right? And imagine you take a data set and you want to do PCA on it. It means that you calculate the covariance of the data set and just do an eigenvalue decomposition of a certain rank on that covariance. Does this answer the question? Yeah, it's exactly like diagonalization of a covariance matrix. Okay. And so in this specific case, let's just imagine that you're doing PCA with a rank 1, right? So, oh, there was another question. Why would you want to maximize the variance of the whole set? The intuition goes as follows. Imagine I give you a bunch of data, right? And you want to compress the data. And your strategy for compressing could be just picking a direction which captures as much of the norm of the original data. And that's equivalent to maximizing the variance after projecting on a certain direction. I don't know if this is answering the question. Does this make sense or it doesn't? No, you don't want to minimize the variance. You want to maximize the variance. Because, okay, imagine you have data, right? And you want to be, the task of compressing, okay, the compression needs to compress the data while preserving the meaning as much as possible. If you just compress everything to a point, you get beautiful compression, but it doesn't preserve your data in any shape or form, right? So you want to compress it into a single dimension, let's say, but you want to keep the variance of the data as much as possible. So here's an example. In this case, we have labeled data, right? And you could just imagine you pick a direction, which is, imagine you were trying to pick a direction that would maximize the variance of the whole data set. Then you can actually prove that this direction is going to be the first principal component of the covariance matrix theorem. And basically, in LDA, you are also picking a direction, right? So in both cases, your task is to pick a direction. But the difference between the two is that in PCA, you're picking a direction that maximizes the variance, whereas in LDA, you're picking a direction that's making the classes as separable as possible by maximizing the SNR. I feel like my choice of discussing PCA was very poor. I assumed you guys knew what PCA was. Are these two directions for PCA and LDA orthogonal? They are in fact not. No, they're not orthogonal. So in practice, if you use linear discriminant analysis, you might get poor performance. For example, if your sample size is low. Why would you get poor performance if your sample size is low? Because if you don't have a lot of data, it becomes very hard to estimate sigma W. Sigma within is hard to estimate because it's a covariance. You need lots of data for your empirical estimate to be a good approximation of the true covariance. Now, another issue that you might have is that maybe this matrix sigma W is not even invertible. Like the rank of the sigma W is upper bounded by how many examples you have in your data set. Let's say you have 5 examples and your data is in 100 dimensions. Then sigma W is not even invertible. So what people do in practice is they either replace the inverse in WC, sigma W minus half, sigma minus 1, UC minus μg. So sometimes you see people replace this inverse right here with a pseudo inverse. I hope some people know what a pseudo inverse is. If you don't, it's okay, forget about it. Or you can replace your within class covariance by a diagonal matrix. So you just take the diagonal. And there's reason in statistics for why you might want to use the diagonal, or why you might want, for example, to regularize your discriminant analysis. So regularizing your within class covariance means calculating a convex combination between your within class covariance and the identity matrix. So all of these things are things that people actually do in practice when they have little data. And these things are helpful if you have little data. And there's theoretical, mathematical, empirical reasons for doing those, but we won't get into them. Now, let me show you an example of what I would consider an interesting paper, which is very recent, surprisingly, 2018, on the topic of linear discriminant analysis. So here's linear discriminant analysis, right? And let's just read the abstract so we see what they're trying to do. This is just a taste of how does linear discriminant analysis appear in the wild? Like, what do people do in the context of linear discriminant analysis? So this paper studies the dimension effect of the linear discriminant analysis and the regularized linear discriminant analysis classifiers for large dimensional data where the observation dimension P is of the same order as the sample size. So if the observation dimension is of the same order as the sample size, it means that your within class covariance is going to be estimated very poorly. More specifically, built on properties of the Wishart distribution and recent results in random matrix theory, we derive explicit expressions for the asymptotic misclassification errors of LDA and regularized LDA respectively, from which we gain the insights of how the dimension affects the performance of classification and in what sense. So in simple words, what they're doing is they're saying, imagine a case where I have high dimensional data, but I have very little data. How does the performance behave as function of these parameters of sample size and dimension? And here's one of the results. So what does this result say? Assuming that the ratio of your P is the dimension of the data and J is just the sample size, right? So imagine NJ is like, 1,000 and P is 1,000. So the ratio is 1. Assume that this ratio tends to a fixed ratio. So this is a very common assumption in modern statistics, in random matrix theory and so on, to those of you who are aware of those fields. And assume that we define y to be y1 multiplied by y2 divided by 1 plus y2. So for example, if you assume that your the number of examples is equal in both classes, what would this value be equal to? If the number of examples is equal in both classes. Half. Yeah, half, that is correct. Because if in both classes you have the same number of examples, then this nj is equal. And then that means that the ratios are equal. If the ratios are equal, it means that this thing is something like, you know, quantity squared divided by 2 times quantity, so you get a half. That is correct. Now, what they're proving is that the RLDA, I think that's the, if I remember correctly, that's the misclassification, tends to the following quantity that might look unappealing to you. Now, what is this quantity? So let's look at what does it depend on. So the first thing you can see here is phi. This is just the cumulative density function of a Gaussian distribution. CDF. Do you remember CDF from probability classes? Do you remember CDFs? And another thing you can see here is that they're doing a sum over the two classes. And can you identify here something that we've discussed in the beginning of the lecture? A quantity that is of fundamental importance in this theorem. A quantity I have claimed was my favorite quantity in this lecture. A quantity that you've now realized is the most important quantity when analyzing linear discriminant analysis. A quantity that can be characterized by a single letter in the Greek alphabet. Yeah, it is the signal to noise ratio. Basically, notice that this whole thing, it's just a function of truly one thing, right? Like the y is not, I guess the y is important, but truly the thing that's most interesting here is delta, right? Do you see delta, 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 delta? What is delta? Delta is defined this way. What is this quantity? This quantity is mu1 minus mu2 multiplied by sigma w minus half multiplied by mu1 minus mu2, right? So what is this quantity? It's just the L2 norm of sigma w minus half mu1 minus mu2 L2 norm squared, right? So what you can see here is that the fundamental quantity on which your misclassification depends on is just how far are the means are once normalized by the noise. Does this make sense? Oh, the limit. So the limit here is taken, basically it's the type of limits that you see in random matrix theory, where you have a set of P, think of it as P1, P2, P3, and so on, and N1, N2, N3, and so on, right? And think of this as both of them are increasing to infinity, but they are increasing such that the ratio tends to a fixed ratio. If this doesn't make any sense, just ignore this. I don't want to confuse people here who are not aware of this type of ideas. But okay, I didn't understand well the difference between RLDA and LDA. How do you modify the problem exactly? So in RLDA, all you do is you just modify the within class covariance by some lambda identity. So you push your within class covariance towards an identity matrix. Certain individuals might refer to this as having a, what's the intuition? The intuition is that if you have no information about your covariance, you should assume it's an identity. That's the intuition. I'm not sure if that's very intuitive. What is the RLDA thing? So RLDA is the usual LDA, except that you replace the within class covariance with this thing. It's enough for you to add any lambda would cause this to be great. When you say greater than 0, the determinant is going to be greater than 0 for any positive lambda that you add. Because the eigenvalues of sigma w are positive, right? Or non-negative would be the correct way to say it. So sigma w is positive semi-definite. So the eigenvalues are all greater or equal than 0. I guess it's a horrible notation. Let's use eigenval. And then if you add lambda to it, it just forces all of them to be equal, greater than 0, sorry. Lambda depends on the ratio somehow. I don't actually remember how do they choose the lambda. I don't remember. Oh, lambda is just a parameter. You can think of it as a hyperparameter. Like use lambda to be equal to, you know, something. Is the confusion about how do you choose lambda, or am I misunderstanding the confusion? Less data implies lambda closer to 1. That is correct. Yes, that is correct, Luke. Because the less data that you have, the worse is sigma w hat, and the better it would be to rely just on an identity covariance matrix. I guess it's not very confusing. Why would you use an identity covariance? But basically, I guess one way to think about this is the following. Imagine if you have lots of data, right? If you have lots of data, then you just use sigma w hat, right? The empirical estimate. If you don't have lots of data, then you say, you know what, I'm just going to impose a structure on the within class covariance, and I'm just going to use the diagonal of sigma w. So I'm just going to zero everything off the diagonal. And it's equivalent to just assuming that the covariance is diagonal, right? And that's by assuming that the covariance is diagonal, you're imposing a lot of structure on the covariance, and it's much better in the low sample size regime. I feel like maybe this doesn't make sense because it relies on a lot of intuition from statistics. There's a formula to life. The formula says the following: the less data you have, the more structure you need. Okay, this is one of those things you might want to put on your hand as well. So if you have very little data, you will only be able to do something if you impose a lot of assumptions. I feel like I'm venturing into philosophical, but it's related to things like regularization, right? If you think about what is regularization, regularization is something that's improving your performance when you have little sample size by forcing some type of structure into the problem. And so using the regularized discriminant analysis is essentially regularizing your covariance by pushing it towards an identity. Why would you assume an identity? Because an identity is, I guess, the simplest covariance one could think of. Like if you have no information, you just assume everything is isotropic noise. Maybe that's the way to motivate it. But my point was that the error of this algorithm, whatever algorithm it is, depends on this fundamental quantity, which is the signal to noise ratio. Does that part make sense? The signal to noise ratio, which is the difference between the means normalized by the noise. And that is the most important quantity in this context if you're interested in predicting the misclassification. Yeah, it is the error, yeah. Where is the lambda in this formula? I think they might have assumed in the paper that they're using some type of a very specific lambda. I don't remember this part. That's a good question though. I think they might have set lambda somehow theoretically to some quantity. In fact, it's possible that when they say RLD, I think they might be referring to the R stands, I think, for misclassification. LDA is the algorithm. So I don't think they even mean here regularized LDA. I think the notation, it's very unfortunate they use this notation because they're using RLDA to mean the misclassification of the LDA algorithm, I think. It's not the regularized LDA. I feel like this might have been very confusing in my presentation. And this LDA algorithm has its limitations, of course. One of the limitations is that the algorithm essentially relies on the class means, right? The class means are what's differentiating between the different classes, right? And you might have cases in real life where the class means are not differentiating your data, but the covariance is differentiating the different classes. Here's an example. You can see there's a blue class and a red class. Both of them have the same class mean, right? But they have different covariances. And so if you used a QDA or something like that, you would have much better success than using LDA. Because QDA, quadratic discriminant analysis, would take into account the covariances of the different classes. And it wouldn't just assume they're equal to each other, right? Another case where LDA might fail is if you have non-Gaussian data. So here's an example of some wacky data, right? And you can see how the class mean is somewhere here. Consider red being flower with petal and sepal and blue being the same flower but positioned upside down. What? Upside down. Petal becomes, I don't actually know what's a petal and a sepal, so I don't know how to respond to that. I feel like I should open a dictionary or something to verify. Yeah, I learned my botanics in Hebrew, so if someone speaks Hebrew and can translate what's a petal and a sepal. For the first case, we can reduce the mean for the data square term to obtain the new data that LDA would be useful. Reduce the mean from the data. You could do some pre-processing that would make LDA better. That is correct, if that's what you mean, yes. And here you can see another example where, again, LDA is not useful. It is not useful. Because in this case, the class mean of the red class is here, and you can see how this is, if you classify based on proximity to this class mean, you're going to do very badly because there's points here, blue points, which are very close to this class mean, and they would be misclassified. So, okay, so to summarize, we've seen the quadratic discriminant analysis algorithm. We've seen how it reduces to the linear discriminant analysis if you make the homoscedasticity assumption. We've seen some important statistical quantities, and that's the thing that you should really take away from this lecture, because those will come very, very soon. These quantities will be appearing in the next few lectures again and again. And the statistical quantities are the global mean, which is mu G, the class means, which are mu C, the between class covariance, which is sigma B, the within class covariance, which is sigma W, and the Fisher linear discriminant, which has no notation, or I guess J. Okay. And so with this, we're now ready to skip or to move to the next lecture. So the next lecture asks the following question. How is any of this related to deep learning? This is a course on deep learning after all, right? How is this related to deep learning? So in order to connect this to deep learning, we're going to talk about a nonlinear discriminant analysis. Nonlinear discriminant analysis. And specifically, we're going to talk about the following paper, which is called The Optimized Internal Representation of Multilayer Classifier Networks Performs Nonlinear Discriminant Analysis. This paper is by Webb and Lowe. Does anyone know Lowe, sorry? Lowe has made significant fundamental contributions to computer vision. Computer vision. So let's read their abstract and see what this paper is about. So this paper says, this paper illustrates why a non-linear, adaptive, feed-forward, layered network, basically a deep net, with linear output units can perform well as a pattern classification device. Very strange words. The central result is that minimizing the error at the output of the network is equivalent to maximizing a particular norm, the network discriminant function, at the output of the hidden units. The first part of the network is explicitly performing a nonlinear transformation of the data into a space in which the classes may be more easily separable. The specific nature of this transformation is constrained to maximize the network's discriminant function. If the targets are approximately chosen, this discriminant function relates the pseudo-inverse of the total covariance matrix and the weighted between-class covariance matrix of the hidden unit patterns. What does this mean? What does this mean? So basically, they're saying that there's some relation between a deep network and some type of a discriminant function. And when they say discriminant function, they mean LDA or something like LDA. And the question is, what is the relationship? Okay, what is the relationship? So let me switch to a writing position and let me illustrate what they've done. So it's actually extremely simple, I think, extremely simple. Imagine that you have a network that is being trained with MSE loss. So the loss of the network is equal to sum over n examples of your classifier W multiplied by a feature. Oh, let me write it like this. Or actually, oops, sorry. Let me write it like this, yes. WHI plus BI minus YI L2 norm squared. Do you recognize here symbols that you like or understand? Hopefully both. So in this case, W is the last layer classifier of the network, the one prior to the logits, right? So what are the logits here? These, does anyone know what are the logits here? If you remember what logits are. What? Wow, you remember. wow. So that is, these are the logits, right? So it's WHI plus the bias, right? There is a bias as well. And YI are one hot vectors, okay? And so imagine that for whatever reason, you've decided that HI, I from 1 to capital N, are frozen. Why? What does it mean frozen? It means that they're not being changed. Someone has coded the network incorrectly. Someone has coded their optimizer incorrectly, and that optimizer does not optimize the layers of the network except the last layer. An honest mistake, right? Mistakes happen. Now, imagine that the only thing that we're going to optimize is W. Oh, sorry, this should be B, not BI. And B are optimized. Does this make sense? So we're only optimizing the last layer and we forgot to optimize the previous layers. So this is basically a least squares problem, right? This is a least squares problem. So let's try to solve this least squares problem. It's just a simple exercise that we've been, hopefully we've done this many times before. Oh, before I do that, let me just introduce a better notation. So here's a simplified matrix notation that I would prefer. So I'm going to write this as W times capital H, where capital H is a matrix which contains in its columns all the different features, plus B times 1 lowercase n transpose. This is a fancy way of writing a matrix where all of its columns are the biases, right? Because the bias is shared across the examples, minus y Frobenius squared, right? Frobenius is just sum of squares, Okay, so now I'm going to calculate the derivative with respect to B, and that's simply equal to WH plus B1 and transpose minus Y multiplied by 1N. This is just a derivative of a standard derivatives. Now, this thing should be equal to 0. Why? Because we're interested in what are the optimal biases and the optimal weights, because there's something interesting that happens, okay? So we just set the gradient to 0. Now, notice that this gives us the following equation. So B multiplied by 1n transpose 1n. So what does it give us if we do 1n transpose 1n? What is that equal to? 1n transpose 1n is equal to, it's just n, that is correct. And that is equal to WH multiplied by 1n plus minus plus y multiplied by 1n, right? Now, notice that this gives us that the optimal bias is equal to minus W H 1n over n plus y 1n over n, right? Does anyone recognize, does anyone have an urge to replace these quantities with alternative quantities? Alternative quantities. can you identify here something that maybe you would want to name a bit differently? A quantity that has appeared just a few minutes ago. Yeah, so the mean of the features appears here. Notice that if you do h multiplied by a once vector divided by n, it's basically equal to the average over I of hi, right? And here, when we do y multiplied by 1, we get just the average over I of yi, right? Now, let us give a name to this average. How are we going to call this average? How would you call this average if you had the choice? If the decision was in your hands and you had to give a notation, delta is the incorrect answer. Sigma is the incorrect answer. Why would you call, no, it's mu, exactly, but it's mu g, right? Okay. Okay, you could call it delta. I'm just saying that because it's a mean over all the features, it's a global mean, right? I didn't mean to insult your names. Your names were beautiful as well. As fine as mu g, if not even more. And also, we want to replace the average over yi with a simple thing. So what's the average over yi? So let us assume that the number of examples in all the classes is equal to each other. Yeah, so Karen says pi, but let's just assume the number of examples is equal, because that's actually necessary for what we're doing. So notice that yi are one-hot vectors, right? And we're averaging one-hot vectors across the data set. So what do we get as a result? So Karen's answer was actually correct. It is pi, but because we're assuming that all classes have equal number of examples, it's just 1 over c, right? Pi is equal to 1 over c multiplied by a once vector, which is now of length c. So this is the optimal bias. What? Now, with this, we must go back to the loss, and we need to plug in this optimal bias, right? So I'm going to do that. So the loss was WH plus B1 transpose N minus Y for B nu squared. And I'm just going to plug in the optimal bias. This is just least squares from linear algebra. So if I plug here, I get, oops, just B, so B, oops, mistake, mu G1 N transpose minus Y minus 1 over C, 1C, 1 N transpose, if I didn't make a mistake. So you can recognize here, this is part of the bias and this is the other part of the bias. Do you recognize, does this make sense? It does make sense. Okay, now notice at this point, we can simplify this expression just by introducing a new intuitive notation. So how would you call H minus mu G 1 transpose if you were to give it a name? First, a verbal name. What does H minus mu G1 transpose do? In simple words, in human words. Yes, it is deviation from the mean. So basically, in human words, I would describe it as features centered by the global mean, right? It's just centering. So I'm going to call the features after centering by the global mean H bar. Bar means globally centered. And also, we're going to have y minus 1c, 1c, 1n transpose. And how would you describe that quantity? How would you describe the second quantity? What is this? In human words, normalized labels. I would say centralized or globally centralized labels, but yes. So it's y bar. That's how I'm gonna denote it. Y bar are the one hot vectors after I subtract their global mean. Now, what should we do next? What is the next thing we do? What will you do next if you had the choice to do something? Minimize over W, that is correct. Thank you, Tristan. So we're going to calculate the derivative of the loss with respect to W, right? And that is simply equal to W H bar minus Y bar multiplied by H bar transpose, right? Again. And by the way, to those of you who are less familiar with how to do these derivatives so smoothly and easily, the answer is there is a wonderful resource called the Matrix Cookbook. Memorize the Matrix Cookbook is my suggestion to everyone, or not. And now we take this derivative and we set it to 0, right? Because we want to find the optimal, no, not Matrix Cookbook, Cookbook. Yes. So we're gonna set the gradient to 0, right? After we set the gradient to 0, we solve for W and we get the following thing. We get WH bar, Peterson, and I'm actually not sure who's the authors, but it's from yeah, Waterloo. Thank you. Yeah. Yes. The reason I mentioned that is because they show how to do derivatives of anything and everything. So it's a useful resource. So you get WH bar H bar transpose is equal to Y bar H bar transpose. And at this point, I'm just gonna multiply on the right by H bar transpose inverse, and I'm gonna get Y bar H bar transpose H bar transpose inverse. And this is the solution. Do you recognize this as being simply least squares? Because this is, no, you don't recognize. But you have seen least squares, right? You have seen, okay. You have seen. So this is just least squares, maybe written in a bizarre manner with bizarre symbols, but it is least squares. Now, at this point, what we're gonna do is we're actually going to massage this expression until we obtain something that is desirable. Could you explain for those who have not seen least squares? Oh, by least squares, I mean minimizing this type of quantities. This is least squares, right? Okay, so we obtained our solution, but we would like to massage it until we get something that is desirable, appetizable. I don't think that's a word. And how are we going to do that? So first of all, let us look at this quantity and let us massage it. So first of all, notice that y bar, h bar transpose, I'm going to instead consider the transpose of that. I like it better. So this is the transpose. Notice that this quantity is in fact equal to h bar multiplied by identity minus 1 over n, 1 n transpose multiplied by y. Why is that correct? Does anyone know? Does anyone know what does this even mean? Definition of y bar. Yes. So one of them is itself, the other one is the center. Yeah, that's one way of putting it. Yes. That is correct, Neo. Yeah. So what Neo is saying is that if you just calculate this quantity, what you get is y minus 1 over n, 1 n transpose times y, and this thing is just this thing multiplied by 1 n transpose, right? Does this make sense? There's actually a name for this matrix right here. Let me highlight it in orange. I feel like we don't use orange enough. How would you call this matrix in orange if you had to give it a name? There's only one correct answer again. If you were to give it a name, how would you call it? A centralizer. It's a centering matrix. Exactly, a centering operator. Yes, centralizer, centering operator. It is a thing. There is a Wikipedia page. So basically, this matrix is just subtracting the CEO. Yes, this thing is just subtracting the global mean from y. Now notice that this thing I claim is actually equal to h bar y. Do you agree or do you disagree? It's symmetric. Yes, it is symmetric. Exactly. Thank you, Tristan. Exactly. So Tristan is saying, is that because h bar is already centered? It is. So basically, if you apply the centering operator, as you've called it, to the matrix h bar, it doesn't do anything because h bar is already centered, right? And so what we're going to do now is look at what is h bar y. So what is h bar y? So let's just plot these matrices. So H has, let's say, P rows, where P is the size of the last layer features. And it has a bunch of columns. How many columns does it have? It has from 1 all the way to capital N, right? Because H is a matrix which contains in its columns the different examples corresponding to your data set. You can see it here. Do you see here? HI goes from 1 to N, and we used all of those HIs. We stacked them into a matrix called H. Should we have a transpose on the Y? That is correct. Thank you for the correction. That is correct. Yes. Now, notice that we can let's assume without loss of generality that all the examples in the first class are here, all the examples in the second class are here, and so on. So this is a partitioned matrix, where the first partition has n over capital C examples. Okay. Now, imagine if we now look at Y transpose. Y transpose. How does Y transpose look like? Let me move this. So Y transpose has capital C columns from 1 to capital C, and the rows are from 1 to n. Moreover, notice that we can partition Y transpose as well in the same manner. And so we can partition it so that in the first n over c rows, we would have the one-hot vectors of the first class. And then we would have the one-hot vectors of the second class, and so on. Now imagine that we try to put here the entries of this Y transpose matrix. What would we get? What would we get? Once in the first column, thank you. Once in the second column, thank you. So basically you would get 1, 1, 1, da, 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 1, 1, 1, da, 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 and so on. And here everything would be 0. Does everyone see this or no? Is this clear? Yes. And so basically we've rearranged the one-hot vectors so that all the one-hot vectors corresponding to the first class appear first, then all these one-hot vectors corresponding to the second class, and so forth, right? Now, at this point, let me ask you, what is this multiplication equal to? Can you use simple words to explain what is this thing equal to? Summing within each class. That is correct. Yes, within class means. That is correct. So the first, by the way, to make it a sum, we need to do here C, or I guess we could write it as 1 over n over c, right? What is the n over c thing again? So we have a total of capital N examples, and we have C classes, so you have n over c examples per class. And we assume that the classes are balanced, so you have equal examples in each class. So what was said in the chat is indeed correct, that this is equal to a matrix where first you have mu1 minus mu g. Then you have, let's just assume it is an integer. Let's assume it is an integer. You're correct that in general you might have, other things, but let's just assume. And then you have mu2 minus mu g, and so on. So this matrix is of size P times C. Why do we have here mu1 minus mu g? Because notice that we're looking at H bar, right? So H bar has a global mean subtracted from all the columns. Does anyone have any questions about this point? Or is this crystal clear? Okay. Now, in what follows, we're going to have a name for this matrix. How would you name this matrix if you had the choice? How would you name it? I feel like I've insulted your names in the previous round of namings, and now no one wants to give names to anything anymore. Is that possible? It's part of the trivia game. Okay, so no one wants to give a name. So we're gonna call it, what? No, we're not gonna call it K. We're gonna use M because M is the capital of mu. And we're gonna use bar because the class means are globally centered. It is a centered mean vector, that is correct, yes, yes. Okay, so this was HY transpose, which was one part of our classifier. And now we're going to look at a different part of the classifier, which is this thing. So it's H bar transpose. So let us massage that expression. So let's look at 1 over n H bar transpose. So first of all, notice that this is equal to sum over I from 1 to n of Hi minus mu g transpose. That is correct, Jack. It is a covariance, yes. Now, notice that we can do a trick that I would suggest writing on your hands as well. This is one of the useful tricks. So what I'm gonna do is I'm gonna add and subtract mu yi. Mu yi is the class mean of the corresponding example. Let me write it like this. Let's do it like this. So mu yi is simply the class mean corresponding to the ith example in the data set. Does that make sense? You think it should be plus. No, but there is a mistake. Okay, let me switch them. Okay, sorry for that. Let me switch. It doesn't. Okay. Now, what I've done was just subtract and add a quantity, and the quantity is the class mean of the ith example. So for example, if for I equal to 1, if the label was class 1, then mu yi is simply equal to mu 1. Does that make sense? Or it does not make sense? Let us think if it makes sense. I see puzzled people, puzzled faces. So what is, okay, how could I explain it? So imagine, for example, you have like this, Gaussian distributed classes, just, for example, and you have here H1, right? Then when I say mu yi, I mean this thing. This is going to be mu I. To each hi, I can assign its corresponding mu yi, which is an element in the set of mu c, where c goes from 1 to capital C. It's just a class mean. Does this make sense? Or still doesn't make sense? Makes more sense. Now, for the same I, though, yeah. I mean, there is a correspondence between hi and the label, right? Now, at this point, what I'm gonna do is just decompose this into 3 sums. So the first sum is hi minus mu yi hi minus mu yi transpose. The second sum is going to be sum from 1 to capital N mu yi minus mu g minus mu g transpose. And the third sum is going to be hi minus mu. I guess I should do 4 sums, but okay, let's just neglect one of them. I don't like one of them. Just do this minus mu yi multiplied by mu yi minus mu g. And then there is a fourth sum, which I don't want to write. Okay. Do you see how this equality holds? Do you see equality? It's just decomposition. So in the first sum here, I'm taking hi minus mu g minus mu yi and I'm multiplying it by this thing. Here, I'm taking this thing and multiplying it by this thing. And here, I have the cross term, which is this thing multiplied by that thing. Make sense or doesn't make sense? Too fast or too slow? Makes sense.
Professor, don't you have two cross terms?
I do, but I got lazy in the second one.
Oh, okay.
I do have two, yeah. And so at this point, we're gonna assign names, our favorite activity today. We're gonna assign names to things. So the first thing we're gonna do is assign a name to this quantity. Does anyone have a proposal? What is this thing? Wow, yes, within class covariance. So we're gonna use the sign sigma w. What do you mean if that's a thing? We just saw a within class covariance in the previous slides, right? So it is a thing. It is a thing. Do you see how this is a within class covariance? Because here you have perturbations. You have perturbations of hi from the class mean, right? And so we're looking at the covariance of the perturbations from the class mean. Does this make sense? Or it does not make sense? It does make sense. Okay, how about the second quantity? Does anyone have a name for this quantity? How would you name it if you were given the opportunity? A between class covariance. Why would you call this thing a between class covariance? Perturbation of class means from the altogether mean. That is correct. This is perturbation of class means from the global mean. And how about the cross terms? Does anyone have any thoughts about the cross terms? What usually happens with cross terms in life? What usually happens with them? Cancel out, they die. Exactly. So why would we ignore them? I guess that's one approach. Yes, you can also ignore them. So how are we going to cancel this out? How are we going to ignore them? How are they going to die? Vanish, disappear, nullify, split the first factor into two terms, left as the exercises were canceled. So there's not possible to be left as exercise. So the reason they nullify is that notice what happens if you consider all of this perturbation for, let's say, yi. Let's say you consider all the examples of the first class, right? If you consider all the examples for the first class, then this thing is just equal to a fixed mu1. And this is equal to mu g, right? Now, what would happen if you consider all the examples in a fixed class here? You would have hi minus mu1, right? And then you would have a sum of y in the first class, right? Now, what is this equal to? Notice that nothing here depends on I except hi. And so if you sum over all the HSs, you get mu1. And so this is equal to 0, 0, 0, 0. So let me conclude, because we're running out of time, by stating the final observation, which is what I was trying to get at. The final observation is that we've proven the classifier is equal to YH transpose H bar transpose inverse. But in reality, we can express this classifier using the terms that we've learned to love and cherish. Specifically, YH transpose is equal to M bar transpose, as we've seen. And there's actually a small scalar here, which is 1 over C, but let's ignore it. And H bar transpose is equal to sigma W plus sigma B inverse. Does this look familiar to you? Have you seen this in your previous 2 hours? Does this strike you as familiar? So this is a cousin. This is a cousin of linear discriminant analysis. It's not linear discriminant analysis, but it's a cousin, because W linear discriminant analysis would have been mean transpose times sigma B inverse. Sigma W inverse. Whereas here you have an extra term, which is the sigma B. So it's a cousin of linear discriminant analysis. And I'll stop here because we're really running out of time. Thank you for joining. And let's stay for questions. Is there any condition on sigma B? What kind of condition? Do you have any condition in mind that you would like, maybe? So sigma B has a rank of C minus 1. That's one condition. Because it's a sum of C elements of C rank 1 matrices, but you have a global mean subtraction which eliminates one rank. Is this a satisfactory condition, or would you like other conditions?
I actually just meant, like, can you just think of any rank C minus 1 matrix as the sigma B and have that correspond to some kind of
there's just one okay, that's first of all a beautiful question. There's one restriction, which is that the null space of sigma B is sigma B has to have a rank 1 null space because the global mean is being subtracted. But besides that, your question is very hard to answer, because you're asking, is there any restriction on sigma B because of the network? So I think you're talking about the previous layers, right? Is that what you're referring to?
Well, assume you only have like a one-layer network. Would there just not be any restrictions?
No. Sigma B is just the between class covariance of the class means.
Oh.
And the class means are just calculated on your data, right?
Okay. Oh, okay, thanks.
Could you say again why the cross terms canceled?
Yes.
Just the equality with 0 there.
Yeah, because notice that this thing only depends. So the only thing here that depends on I is HI, right? And so because of that, you can push the sum into here, into the HI. Or it should be an average if I were to do it properly.
Oh, I see. I see. The 1 over n. Well, wait, don't we have an issue with the 1 over n though? I mean,
so let's do it more properly. Let's put it 1 over n over c. Okay, that's more proper. So okay, so let's apply this onto HI. Do you agree that this would give us mu1? Or no?
Yes.
You do? Because you're summing over all HI where I is restricted to be in the first class, and then you're normalizing by the number of contributions. So that's mu1. And then notice that doing an average of a fixed vector doesn't do anything, right?
Oh, I see. Right.
It's actually, I can do something simpler. Here's a simpler explanation. Imagine if you look at 1 over n, let me just do something simpler. Xi squared, I from, and let's do minus, I'll do something which is analogous. So this is an empirical second moment of a scalar. Now notice that you can do 1 over n, sum over I from 1 to n, and then I do xi minus, and then I do average over I of xi squared, right? Oh, and sorry, I should do plus average over I xi, right? So I haven't really done anything. And now notice that this is equal to 1 over n, sum over I from 1 to n, xi minus the average over I xi squared plus 1 over n, sum over I from 1 to n, average over xi I squared, and then plus or minus, I guess, minus, plus, minus, plus 2 over n, sum over I from 1 to n, xi minus average over, oops, average over I xi multiplied by average over I xi. Does it make sense so far?
Yeah.
And so here, notice that this thing is just a variance. This thing is just a mean squared. And this thing is just equal to 0. Because I guess I should have used here j or something to avoid confusion. Because your sum, your average is just going to apply over the xi's. So basically this thing would be equal to this thing, the last thing would be sum from I from 1 to n xi minus, I guess you could do 1 over n sum over I from 1 to n average over xj times average over xj. And so this thing is equal to average over xi minus average over xi multiplied by average over xi. Does this make sense?
Right. Yeah.
You can also do this like in continuous probabilities. This just expectation of x squared is equal to expectation of x minus expectation of x squared plus expectation of x squared, right? Then you get expectation of x minus expectation of x squared plus expectation of x squared. Does this look familiar? Plus expectation of x minus expectation of x times expectation of x. I think this is something one sees in probability.
Right. I tried to forget, but
You
yeah,
try
that
to
makes sense.
forget. Yeah, and then this is like a variance. And this is a mean squared, and this is 0.
Right.
And the only difference between this and the previous thing is that here it's a bit more complicated because you don't have a single mean, you just have a bunch of means associated with the classes. So it's a bit more tricky.
Would you be willing to post these, like a PDF of these notes, even on like Quarkus or something?
They are on the website.
Like this this notebook here?
Not this one, a more elegantly typed version. I feel like it's very hard probably to understand this barbaric handwriting. So I typed it in Beamer.
Oh, got it.